Good evening, all. Okay. So, yesterday we have started Turing machine and we started the design part also. I have given you one question. Hope you have solved that question. Okay. So, guys, by Sunday, yeah, Saturday, not Monday. By tomorrow, not possible. By Sunday, I'll complete that TOC. Today, I'll take 6 to 9, 3 hours. Tomorrow, 3 to 10. Are you following? Tomorrow class is 3 to 10 and Sunday also 3 to 10. Okay, chalo. So, yesterday we have done this question. So, you understand? Somebody has given the solution. They are correct. Now, here sigma is A comma B. Take a string of combination of A and B. Any combination of A and B. Okay, na? Any combination. It can start with A or B. Okay. So, I am starting with A, or take A, B, B, A, B, A, B, A. Let us take this one. In Q naught, before and after blank will be there. Okay. In Q naught, A comes. In Q naught, A comes. A will be A only. Move right side. Same state, Q naught. Okay. Then again A will be Q naught on A. A will be A only. Move right side. Again Q naught A. A will be A only. Move right side. Now, so A will be A right side. Now Q naught. B will be B. Move right side. Go to Q1. Now, Q1 we have not defined anything. Are you following? In Q1 we have not defined anything. Therefore, the machine stops here. Are you following? Q1 as we have not defined anything. I repeat. In Q1 as we have not defined anything, the machine stops in Q1. The machine stops in Q1. Hello guys, here there is still some input is pending. Input string is not scanned completely. No problem. What did I say yesterday? Starting at initial ID, whenever machine stops, if it stops in a final state. Are you following? Starting at initial ID, if the machine stops in a final state, yes, Q1 is a final state. Whether the string is completed or not completed doesn't matter. So as it stops in Q1, it is accepted. So it is accepted. Therefore, this is the machine accepts. So from year to year, from initial to final, minimum 1 B must be there. Before that, it can have any number of A's, maybe 0 or more A's. After that, any combination of A and B. So A star B, A plus B whole star. A star B, A plus B whole star. This is the expression. Okay. Saurya Bhatnagar, 2 questions. How complement of language WW, where W is a string of A and B, is context free. Okay. And what is encoding of Turing machine? Encoding of Turing machine, I will tell you now. Okay. And complement is a workbook question, you can see. Encoding of Turing machine, I will tell you. Don't worry. So here any number of A's followed by at least one B, then combination followed by any combination of A and B. This is the language accepted by this machine. Okay na? I'll give you one more design. You please tell me. Okay na? This is first question and second question. Tell me, what is the language? Yeah, substring. Ankit Gol, you can say, no problem. Substring B or at least one B, that is best. Good. Good. Very good. Aftab Ansari, wrong. Yeah. Subi Goyal, you are in full form. Okay, guys. Listen. Good, guys. Very good. Here, any number of A's, then say Q naught on A will be A, move right side, same state. Again Q naught on A will be a right side, Suppose after A blank, Q naught on A will be A right side, same state, Q naught. Q naught is not defined for blank, it stops here. So Q naught is non-final, not accepted. So here to reach the final state, Q2, you must have 1B. So if there is a B, Q naught on B will be B right side Q1. If again B comes, Q1 on B, it is undefined. Okay? Q naught on B, it comes to Q1 on B, it is undefined. When it is undefined, the machine stops here. Are you following? Q naught on B, it goes to Q1. B will be B, right side Q1. Q1 is undefined for B, the machine stops here. Are you following? Now, so when machine stops here, means it is a non-final, not accepted, not accepted, not accepted. Suppose in see Q naught on B, it goes to Q1, and in Q1 if it is blank, yes, blank will, these are all blanks. Blank will be blank, move right side, blank in Q1 blank will be blank, move right side, go to Q2, and Q2 is a final state. Therefore, the machine here Q2 is undefined for anything, it stops here, and final state. So accepted. So here one any number of A's followed by single B. This is the answer. So here if this is the final state, any number of A's followed by B followed by any combination of A and B. But here any combination of A and B, the machine stops in Q1. If blank comes, then only it goes to Q2. When the blank comes, after single B, if blank is there. So any number of A's, A star followed by B, single B. Okay. Ritu, you are not giving any answers yesterday also. Chalo, we'll go to next design. Okay. Third question. Design a Turing machine. Over set 0, 1, which can produce the output as first one, one's complement and two's complement, second one complement of the input string. So you know how to do the one's complement, two's complement, because we have done in the finite automata. Okay, try. Okay, now look at this, guys. It is very easy. One's complement. What? If this is the input 1 0 1 1 0 1, what is the output? Should be 0 1 double 0 1 0. So what guys? Very simple. Very simple. Okay. So here 0 comes, 0 will be 1, move right side. Yes or no? Or if 1 comes, 1 will be 0, move right side. Okay? 0 will be 1 right side, 1 will be 0 right side. Until it blank comes, it moves on. When blank comes, I don't define in Q0, the machine stops in Q0. The machine stops in Q0. If you want to terminate, you can, of course it will terminate here only when the blank, when in C. So here see, Q, here, actually it is not. Here, what happens? What happens here? Here, the machine scan this, it will be 0. It will be 0. It will be 0. Okay, 1 will be 0, 0 will be 1, 1 will be 0, 1 will be 0, 1 will be 0, 0 will be 1, 1 will be 0. When blank comes, the machine stops. And Q0, undefined for blank. Yes, the target is finished. So, this is the answer. Okay, na? So, need not to go for any final states. No problem. It's 2 states. 2 states means you might have taken this extra. Okay, na? Like this is on blank, blank will be blank, move right side and stop. No problem. It's not required, not necessary. Chale, this is 1's complement. What is the 2's complement? Now listen. So what is the 2's complement here? 2's complement. This is 1's complement, no? 2's complement. Suppose I told you one logic. Example, the input is like this. The input is like this. the input is like this 1 0 0 1 0 1 0 1 1 0 0, example this one. So I told you na, in the case of Mealy and Moore mesh design, what we do, we'll go until the end, this is the blank. So we go until the end, blank comes. When blank comes, come to right side, this 0 will be 0, 0 will be 0, 0 will be 0 until you get the first one. The first one you keep it, this one you make it as 0, 0 will be 1, 1 will be 0, 0 will be 1, 0 will be 1, 1 will be 0. This is the answer. Okay na? I told you this. Okay na? Next. So, Madam Mishra, how patient you are. You have so much of patience. Now listen guys. So here, as long as 0 or 1 comes, 0 will be 0 right side, 1 will be 1 right side. Okay na? So 0 will be 0 right side, 0 will be 0 right side, 1 will be 1 right side, 0 will be 0 right side, right side, right side, right side. Kab tak? Until you get the 1. Okay na? Sorry, blank. So 1 will be 1, 0 will be 0, 0 will be 0, 1 will be 1, so on, right side. When you get the blank, so here see Q0 and 0, we will go to right side. So 1 will be 1, 0 will be 0, 0 will be 0, right side, right side, right side, 0 will be 0, right side, blank. When blank comes, move left side, come to its Q1 state. Here what is the logic? In this here, when we come to Q1, when we come back Q1, here what is the logic? You keep the 0 as it is. 0 will be 0, 0 will be 0, 0 will be 0 until you get the 1. 1 also will be 1. Okay. Now what I do here, when you come left, 0 will be 0 left, 1 will be 1 left, 0 will be 0, 0 will be 0, 0 will be 0, 1 will be 1. Then from here, so 0 means don't scan. So what I mean to say here, okay, so here this 0 will be 0 left, 0 will be 0 left, 0 will be 0 left, 1 will be 1 left. Now here see, actually 1 will be 1 left, you have to change the state na. Otherwise again this 1 will be 1, 0 will be 0, 1 will be 1, so nothing will be difference. So you have to delete this. Okay, so in Q1 this is Q0. In Q1 0 will be 0, 0 will be 0, 0 will be 0. When 1 comes, you change the state, otherwise it will be as it is. Okay, so in Q1 1 will be 1, 1 will be 1, 1 will be 1, move left side and go to Q2. Okay now, what is the logic here? So until blank comes, go to right side. When blank comes, move Q1, 0 will be 0, 0 will be 0, 1 will be 1, then left side go to Q2. Why? Because from here you want to complement. So 0 will be 0, 0 will be 0, 0 will be 1 left side, 1 will be 0 left side. Complement करना है ना. So here 1 will be 0 and 0 will be 1 left side. This is the design. Okay, I think you got the same. Hello, Subhi Goyal. To accept a string, compulsory final state required. Here we are not accepting. We are working as a transducer. These are all here see, we have taken the final state because it is accepting. Here it is also final state accepting. So to accept the language, final state compulsory. If it is working as a transducer, one's complement, it is not accepting, two's complement not accepting, so no, final state not required. Okay na? Now I'll give you one more question. Copied this one, guys. Good. Okay. Now take the question. Design a Turing machine. Design a Turing machine over set 1 which can copy the means which can add the two input strings, which can add the two input strings. That means here suppose input is like means if W1 equal to 1 1 and W2 equal to 1 okay, then we pass the input as like this, W1 blank W2, then output must be W1 W2, output must be W1 W2. Okay, this means guys, suppose if this is the tape, okay, now here the W1 is 1 1 and a blank, W2 1 these are all blanks. So if this is the input will be given in the tape as W1 space blank then W2. So the two input will be passed like this. So whenever you give the two inputs, the Turing machine takes with the separation of one blank. Okay. Now if this is the input, then what must be the output? The output must be like this. If this is the input, the output must be like this. Output must be, so here this is blank 1 1, this blank is there na, this blank should be eliminated, and 1 1 1 1. Actually what is the input here? Input is here 1 1 blank 1 1 1. Output must be 1 1 followed by 1 1 and the remaining all are blank. This must be the output. Okay na? Kar lo, just try. Okay, now listen. Very simple guys. Very simple. So, what is the logic here? You start from here. 1 will be 1. 1 will be 1. 1 will be 1. Go to right side. 1 will be 1 right side. 1 will be 1 right side. Whenever we get the blank, that blank we will convert into 1. Okay. Then, how many ones we have? Extra 1. Then you do one thing. Come back to the first until you get the blank. Then move right side. Then isko blank karo. That is one way. Otherwise, go to right side until you get the blank. When blank comes, move left side. Then this one you convert into blank. Anyway, you can. So convert this one into blank, which is blank into 1. Move right side until you get the blank. That blank, you keep it as it is. Come to left. That last one you convert into blank. Otherwise, you convert this blank into 1. Move left side until you get the blank. Then move right side. This one you convert into blank. Anything is okay. Okay na? Now you can go for anything. So here 1 will be 1, 1 will be 1, 1 will be 1, right side. Okay, 1 will be 1, right side, 1 will be 1, right side. Kab tak? Until you get the blank. Okay, until you get the blank. Okay guys, so when blank comes, blank will be what? This blank will be 1. If you move left side, okay, or you can move right side. Anyway, okay na? So what I have done, so this blank, I have converted to 1. Move right side, move right side, right side, right side, right side until you get the blank. So this blank will be 1. I will change the state. Here I will keep on moving. I will keep on moving right side, right side, right side. Are you following? This 1 will be 1, 1 will be 1, blank will be 1, move right side, change the state. 1 will be 1, 1 will be 1, 1 will be 1 until you get the blank. When blank comes, what shall I do? When blank comes, what shall I do? Blank will be blank, blank will be blank, okay? Blank will be blank, move left side. When blank comes, you keep the blank as it is, move right, left side, then come to this. Now we are at the last symbol and we are at the last state. So I want to convert this one into blank. So that one will become blank. This one you convert it to blank and move left side. If you move left side, we are in the same state. Entire will become blank. So that is the reason. Move right side. इसको blank करो, then move right side, and we are in this. We have not defined blank. The machine stops. But target is finished, na? That is the design. Okay. Parth, Abhishek, Manoj, Abhijit, Manoj, Madhav Mishra. Oh. Okay, Abhijit. You can replace Ankit Gwal, blank or any symbol with anything you can replace. Okay, Ankit? Question slide, this one. Okay. Next, we'll go to next question. चले next. So guys, this is okay. Now we will go to the next question. Now listen. Design. So listen this carefully. Design a Turing machine for L equal to 0 power n, 1 power n, n greater than 0. Okay, na? Guys, this is not a regular. Okay. Guys, design a Turing machine for L equal to 0 power n, 1 power n, n greater than 0. Here this is not regular because it is relation, comparison between zeros and ones and infinite. Comparison infinite. So this is not regular, but it is a fine context free language. Why? We can do that PDA. We can consider the PDA. PDA is very easy. What is the logic? We'll push all the zeros. We push all the, suppose 000, 111. We push all the zeros. Suppose one more zero. Push all the zeros. When one comes pop, one comes pop, one comes pop, one comes pop, and epsilon z0. So accepted. So the design of PDA is also very easy. But finite automata we cannot construct, so not regular. But the design of PDA is very easy because it's simple, push zeros when one comes pop. But here in Turing machine there is no stack, only tape, but read and write tape. So how to do? Look at this, guys. This is, listen carefully. Don't type any message. Okay, na? Don't type any message. All your doubts will be cleared slowly. Okay, listen carefully. Because this we cannot construct the PDA. PDA is not possible because same comparison. Zeros has to compare with 1, zeros has to compare with 2. Same comparison multiple times, not possible. But you can consider a Turing machine for this. Not only for that, you can consider for 3 power n, 0 power n, 1 power n, 2 power n, 3 power n, 4 power n, 5 power n, 6 power n. All these we can consider a Turing machine if you can understand this design. Okay, na? So slowly I will tell you. But for all this, you cannot consider the PDA. You cannot consider the PDA. So slowly I will explain. Listen, guys. Okay. Now suppose there is a string 00011. I want to accept this string using Turing machine. Very simple, guys. So whenever you scan, the first symbol must be 0. So what I do? This zero. I will convert into X. Are you following? The 0 I will convert into X. Then I will move right side. Again right side. So I keep on moving right side until I get the 1. Are you following? Until I get the 1. So X will, 0 will, first 0 I will convert into X. Then I move right side. This 0 will be 0 right side, 0 will be 0 right side, then 1. When 1 comes, what is the logic actually? I will tell you logic first. Okay. So suppose there are zeros. It can be any number of zeros. And whatever the number of zeros, that many ones has to be there. Yes or no? What is the logic here? We convert this 0 into X. We move right side and we convert this 1 into Y. Then again we come back until we get the X. Okay, we come back. When X comes, we move right side. Then this 0 we will convert it to X. Again we move right side until we get the first one. Then this one will become Y. Then again we move left side until we get the X. Then when x comes, we move right side. This 0 will become x. Again we move right side until you get the 1. And when 1 comes, we will convert into y. Then again left side. So what is the logic here? Simultaneously 0 को x करो, आगे चलो, 1 को y करो, पीछे आ जाओ, पीछे आने का ना. Example this one. So what is actually this we have converted into? This we have converted, okay na? So x, here y. This last one, this one. When we convert into y, we will come back until. So what is the next logic? What is the next target? You have to convert this 0 into x. What is the next target? You have to convert this 0 into x. So this 0, how do we know this is the first leftmost 0? Every time leftmost 0. So how do we know the leftmost 0? Is this the leftmost 0, or is this the leftmost 0, or is this the leftmost 0? We cannot know. So what we do, we will come left side from here, come left side until you get the x. When x comes, what I do, we will move right side. So this will be the first 0, leftmost 0. Then what we do, we convert this into x. Then we move right side until you get the first one. When 1 comes, we will convert this into y. Then we move left side until you get this side first x. Then when x comes, we move right side. Then again we repeat the procedure. 0 will be x, move right side, 1 will be y, come back, 0 will be x, then 1 will be y, come back, 0 will be x, 1 will be y, right side, simultaneously. And finally, if all zeros are become x, and here also definitely all ones will become y if ones and zeros are equal. And see, last one, when I convert into y, I'll come back. When I convert this one into y, I'll come back until I find the x. If x comes, I'll move right side. Actually, until the previous one, whenever I move right side, it was 0. But what is here? It is y. Means what? Zeros are finished. If zeros are finished, ones also must be finished. Why? Because simultaneously 0x, 1y, 0x, 1y, 0x, 1y. So simultaneously we have converted. If zeros and ones are equal, all ones also become y. Then we will check any ones are remaining or not. So we will move right side until you get the blank. If blank comes, that indicates ones and zeros are equal. So if zeros and ones are equal, every one will become y. Then after y, only blank will come. When blank comes, we will go to final state. Okay na? Even though you didn't understand whatever I said till now, don't worry. I will repeat this story again. Look at this. Suppose okay, now listen. We want to, this is 0 cube, 1 cube, valid. Okay na? So before and after, any number of blanks will be there. We want to check. Look at this 0 cube, 1 cube. I am doing the logic. We start from the first symbol. When 0 comes, 0 will become x. Move right side until you get the 1. When 1 comes, this one will become y. After that, move left side, move left side, move left side until you get the x. When x comes, move right side, move right side. Now we are at the leftmost 0. Then this leftmost 0 will become x. After becoming this, converting 0 into x, move right side until you get the 1. When 1 comes, convert that 1 into y. After that, move left side, until you get the x. When x comes, move right side. So this is the 0. This 0 you convert into x. Then move right side, until you get the 1. When 1 comes, that 1 you convert into y. After converting this 1 into y, move left side, until you get the until 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 you move left side until you get the x. When x comes, move right side. Hello. Now until we move to the right side, in earlier cases we got the 0, but zeros are finished. So that is the reason we got the y. Means when we get the y, when we move right side, if all zeros are converted into x. If all zeros are converted into x, as we are simultaneously converting 0x 1y, 0x 1y simultaneously, if all zeros are converted into x and all ones also must be converted into y, you can see. So if we have to check whether any ones are remaining or not. If any ones are remaining, we will stop, we will don't go to the final. If no ones are left, means every one is converted to y. After that, then after y, there must be a blank. So here what we do, whenever one y comes, we move right side, y will be y, right side, right side, blank. When blank comes, go to final, and final में stop करो. Okay ना? So just try this logic. I'll give you 2 minutes of time. See, oh, 0 will be, so what is the logic here? 0 will be x, then move right side, change the state, okay na? 0 will be x, so this 0 will be x, this 0 will be x, move right side. What is the next target? We have to move right side until you get the, so 0 will be 0, 0 will be 0 right side, 0 will be 0 right side until you get the 1, okay na? When 1 comes, that 1 will become, this one will become y. After that we will come back, means left side. So here when 1 comes, 1 will become y, move left side. So this is Q0, this is Q1, this is Q2. Q0, this is Q1, this is Q2, okay na? After that, what is the logic? 0 will be 0 left side, 0 will be 0 left side. Are you following? So 0 will be 0 left side, 0 will be 0 left side. So 0 will be 0 left side, 0 will be 0 left side until you get the x. When x comes, you have to move right side and you have to come to the initial position. That is the reason in Q2 x comes, in Q2 x comes, keep the x as it is. X will be x right side, x will be x right side, okay na? This x will be x right side. The machine go to right side, means the head goes to right side, Now we came back to the initial state Q0, okay na? First 0 we made it as x, then move right side, 0 will be 0, 0 will be 0. When 1 comes, 1 will become y, move left side, go to another state. In that state, 0 will be 0, 0 will be 0, 0 will be 0, 0 will be 0, 0, 0, 0 left side until x comes. When x comes, we see in Q to x come, x will be x, then move right side, but come to Q0. So again we are in the starting Q0. What happens in Q0? This will become x, it move right side, 0 will be x, move right side, go to Q1. In Q1, what is the next target? You have to move right side until you get the 1. So here 0 will be 0, 0 will be 0 right side, and y will be y right side. So y will be y right side. So in Q1 we keep on moving until 1 comes. In Q1 1 comes. Are you following? In Q1 1 comes. So 1 will be y, 1 will be y. So in Q1 when you get the y, move left side, go to Q2. So after 1 converting this 1 into y, left side. So but go to Q2. So here what will be y? Y will be y left side, 0 will be 0 left side until you get the x. When x comes, again come back to Q0, but go to right side and go to Q0. In Q0 what happens? This Q0 will become x, move right side, go to Q1. In Q1 y will be y until you get the 1. In Q1 when 1 comes, 1 will become y. When in Q1 1 will become y and move left side, go to Q2. What is the here? Y will be y right side, until you get the x in Q2. When Q2 x comes, x will be x, move right side right side and come to Q naught. Now guys, have you observed? Q naught, what is the input symbol? Y. Why we get the Y? Because zeros are finished. When zeros are finished, as we have converted zeros and ones simultaneously, if all zeros are converted into X and ones also must be converted into Y. If all ones are converted into Y, then Y after you must get the blank. So for that reason, here when in Q naught, when you get the Y, we move right side. So Y will be Y, right side, Q naught. Y will be Y, right side, Q3. Y will be Y in Q3. Y will be Y, right side. In Q3, Y will be Y, right side. Okay. Y will be Y, Q3 right side. So in Q3, Y will be Y, right side, Y will be Y, right side in Q3. In Q3, you will get the blank if and only if. In Q3, see Q naught Y comes, we move right side Q3. Y will be Y, right side, Y will be Y, right side. In Q3, when blank comes, that indicates zeros and ones are equal. In Q3, if blank comes, then we go to final state. In Q3, if blank comes, then we go to final state, and this is blank will be blank, right side. And final state, I don't define anything. In final state, I don't define anything. The machine stops here because it is as it is stopped in final state, it is accepted. Okay na? So copy this, guys. Aftab Ansari, if you put on self loop 0, x right side, then entire zeros will be converted to X at a time. But as per the design, you have to simultaneously 0x, then move forward 1y, then come back. So if you write self loop 0, x right side, so every zeros will be converted to at a time X. Okay guys? No, Abhijit. That is not correct. The problem is, if you do like this, 00011, again 0011, this will be accepted, which is not correct. So you cannot do like this, which is not correct. This is not correct. If you do like that, it will be accepted. Okay? Now we'll go to next question. So guys, design a Turing machine. Design a Turing machine. Design a Turing machine for L equal to 0 power n, 1 power n, 2 power n, n greater than 0. Hello guys, this is not a regular and not a CFL, because same comparison, zeros must be compared with 1, same number of zeros, whatever the number of zeros, that many number of ones and that many number of twos. So same number of zeros you must compare with 1 and you must compare with 2. Same comparison, any same comparison required more than one time. It is not CFL. And okay, this is not CFL, but you can construct a Turing machine. How? Same logic. 000, 111, 222. You do one thing, okay? You just convert this 0 into x, then convert into y, then convert it into z, then come back. Then again this is 0 into x, 1 into y, 2 into z, then come back. This 0 into x, 1 into y, 2 into z, come back until x comes. When x comes, move right side. Then check whether any ones are remaining. Then y will be y, right side. Then z will be z, z will be z, z will be z. When blank comes, go to final state. Karo, you do this one. Okay, done? Done, guys? Look at this one. I'll do. Guys, look at this one. Initially 0 comes, 0 will become x right side. Suppose there is a 0, 0, 0, 1, 1, 2, 2, 2. This is the string. Okay? Zero, 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 1, 1, 1, 2, 2, 2. So what we do? With this, we convert this 0 into x. This 0 into x. Then move right side. Then scan the remaining zeros. 0 will be 0, right side. 0 will be 0, right side. 0 will be 0, right side. When 1 comes, this one convert into y. So convert 1 into y, move right side. Right side. So 1 will be 1 right side. 1 will be 1 right side. Okay na? So here, first one it will be y. Then move right side, change the state. Then 1 will be 1 right side. 1 will be 1 right side until you get the 2. When 2 comes, this 2 we convert into z. This 2 we convert into z. Are you following? This 2 we convert into z and move left side. So here 2 will become z. 2 will become z left side. After that this, okay na, left side, left side, left side. So keep on left side, keep on moving left side, keep on moving left side. So here 1 will be 1, 1 will be 1 left side, 1 will be 1 left side, y will be y left side, y will be y left side. Then 0 will be 0 left side, 0 will be 0 left side until you get the x. When x comes, x will be x right side. X will be x right side. Okay na? So guys, when x comes, we come to this q0 and 0. 0 will be x. 0 will be x. Then move right side, q1. In q1, 0 will be 0. Then y. Y will be y right side. Okay na? Then this one will become y, move right side. 1 will be 1 right side. Z will be z. Here z will be z right side until you get the 2. When 2 comes, 2 will become z and move left side. Move left side here. Then z will be z, 1 will be 1. So z will be z. Z will be z. Okay na? Z will be z. Move left side. Move left side. 1. 1 will be 1. Okay na? Then y will be y. Y will be y. 0 will be 0. 0 will be 0. X. When x comes, again come to right side, go to q0. In q0, this will become 0. Sorry, this 0 will become this 0 will become x. Then it comes here. Then y will be y, y will be y. This 1 will become y. Okay na? Then it comes to q2. Z will be z, z will be z. Then this 2 will become z. Then it comes to right side, right, left side until you get x. When x q3 comes, in q3 x comes, it move right side, go to q0. Now the machine is in, okay, the machine is in q0, but input symbol is y. Y comes means what? all zeros are finished. If all zeros are finished, you have to check any ones are remaining or not. Any ones are remaining or not. So for that, in Q naught, y comes. Y will be y right side. Go to the next state. Then here. Here we will check any y's are remaining or not. Y will be y right side. 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 Then z will come. So you can check. Here one state is enough. Z will be z right side. Z will be z right side. If no z's and no ones or no twos are left, you will get the blank. When blank comes, keep the blank as it is. Blank will be blank. Blank will be blank. Move right side, go to final state. This is the design. Okay, so check. Actually, hello. Here, see, in the previous machine, when y comes, we have to move to Q3 to check whether any ones are remaining. The same procedure here also. See, suppose here all zeros are finished. Then when Q naught y comes, so you check whether any ones. No, y will be y right side, y will be right side. Then no ones, then z will be z right side. Then blank means this is in the form of 0 power n, 1 power n, 2 power n. Then only you will get the blank. And blank comes, you go to final state. Okay, this is Rask Mishra. Okay guys, so that's all guys. We have done the design part. We'll go to next one. So tomorrow class is from 3 to 10. Tomorrow 3 to 10. Okay, and day after tomorrow also 3 to 10, and Monday also. So Sunday I will complete the TOC. Sunday I will complete the TOC, and Monday onwards compiler design 3 to 10. From Monday onwards compiler design 3 to 10. So only the students who have not attended for the CD class, they are only allowed, and already those who have attended, I think you don't get the access. Okay, so Sunday will be the last class. Okay, now this is about the design part. Now we'll go for next. Variations of Turing machine. Variations of Turing machine. Variations of Turing machine. Now, what are the different types of Turing machine? Okay. First one. First one. Multi-track Turing machine. Sunday class timings is 3 o'clock, from 3 o'clock. I don't know about the OS. Maybe after this CD, you may have the OS or discrete mass. I don't know. Okay. So multi-track Turing machine. What is multi-track Turing machine? There will be multiple tracks, that is multiple tapes, this is infinite. Okay, suppose this is the input string A, B, B, A, and these are the blanks. Suppose this is B, A, B, B, blank, and suppose all these are blanks, let it be. Okay, so in multi-track Turing machine, there will be a single tape, single head, single read or write head, multiple tapes. It has multiple tapes. It has multiple tracks and single read or write head. Suppose the machine is in Q naught. It takes B from the first tape, takes A from the second tape, takes blank for the third tape. Okay na? Q naught B A blank. After that, what is the next state? And B will be replaced by X, suppose, and A will be replaced by Y, suppose, and blank will be replaced by Z, suppose, and left and right. So like this. Okay na? So even though it has multiple tracks, the power means the performance, either in acceptance or in means as a transducer, the power is same as standard Turing machine. Okay, take. Okay, done. Now, copied. Okay, next. This is multi-track. Okay, na? Next, we'll go for multi-tape. Multi-tape Turing machine. So, multi-tape, there will be a multiple tapes and multiple heads. Suppose here this is infinite. So there will be multiple tapes and multiple heads. So it has multiple tapes. Multiple tapes and multiple heads. Even though there are multiple tapes and multiple heads, so the power is same as standard Turing machine. The power is same as standard Turing machine. The power is same as standard Turing machine. Okay, you take this one. These are the different kinds of Turing machines. Just what is enough. You need not to go for in depth. Multiple heads, multiple read and write heads only. Okay, na? So here multiple head means multiple read or write heads. Don't get any confusion. It is multiple read or write heads. This is multi-tape Turing machine. Okay, it has multiple tapes and multiple reader heads. The power is same as standard Turing machine. Done. Then next, multi. So we have seen multi-track. Tracks are multiple, head is same. Okay, single head is single. In multi-tape, tapes are multiple and heads are also multiple. Then multi-dimensional. 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 Multi-dimensional Turing machine. What is this? Here okay, so multiple tracks will be there. This is infinite. Okay, this is infinite. Suppose at any time, suppose here it is reading this symbol. After reading this, it can go to left. Generally, the machine go to either left or right, na? Left or right. But here, multi-dimensional. It can go up and or it can go to down also. It can go to left, it can go to right, it can go to up, it can go to left also. So del of Q naught comma A. Okay. So you can here it can go to left or right. So we can represent like this: q cross tau into what is the next state, what symbol, the present symbol, it is scanning this na, so what symbol, the symbol is replaced, and the direction left, right, up and down. So you can say like this: left or right or up or down. So this is the trans function mapping. So copy this. And power is same as, all these are power is same as standard Turing machine. The power is same as standard Turing machine. Standard Turing machine. The power is same as standard Turing machine. Okay. Then next. Okay. Okay, next, multi-head Turing machine. Multi-head Turing machine. Multi-head Turing machine. So this is infinite. Okay. What is multi-head Turing machine? It can have multiple heads. Okay, na? So like this. So there will be a multiple heads, and each can scan any symbol. Example A, B, B. This is A, B, B. And example the blank, and this is blank, and this is blank. Okay, so here this head, after scanning, it can move left or it can move right. After scanning, it can move left, it can move right, and this also it can move left or it can move right. So individually, not always all are move left side, all are move right side, not like this. Yeah, anything can move left side or right side after completion of. So here the same symbol can be moved by one or more heads also. Suppose after some time all heads are scanning this input symbol, then the first head says I will replace, for the first head says I will replace A with X, second head says I will replace A with Y, and third head says I will replace A with Z. Are you following? These can move, every head can move individually, it can move left side or right side. Suppose a symbol sometimes may be read by two or more heads. So suppose in this at this position all three heads are scanning A, then the first head says that I will replace A with X, the second head says that A will be replaced by Y, and third head says that I will replace A with Z. Then what will be the output? Then there will be a priority will be given to the heads. Priority. Whatever the highest priority, that output will be taken finally. Suppose head 1 is the highest priority, then A will be replaced by X. Otherwise, if head 3 is the priority, highest priority, then A will be replaced by Z, like that. Okay, na? So multiple single tape. It has single tape. It has single tape and multiple heads. Multiple heads. But power is same as. The power is same as standard Turing machine. The power is same as standard Turing machine. Copy. Any heads depends. Bah. Subhi Goel, you will get. If it is multiple heads, if it is fixed, I will say na. Next. Turing machine with semi-infinite tape. Semi-infinite tape or one-way infinite tape Turing machine. One-way infinite tape Turing machine. One-way infinite tape Turing machine. Take power means anything. Language accepted or performance or a computation capacity, all will come. Power means the language acceptance, the computational capacity as a transducer or as an acceptor, all. The Turing machine with semi-infinite tape or one-way infinite tape. It can give you the, okay, so one way means the other way we will fix. So only one way is allowed. Only one way is allowed. So guys, one way it is blocked. The other way it is infinite. This way it is infinite. Okay. This is infinite in other way. Are you following, guys? This is infinite in only one way. The other way it is fixed. So it cannot go to beyond this one. Okay na? So, and here the head will be there and this is the input string. So there can be blank also. A, B, A, blank, blank, so on. So here it is one way infinite tape, then the other way, and the other end it is fixed, means you can say closed. Okay na? So the power is same as standard Turing machine. Okay. So the standard Turing machine is two way, but here it is only one way. Okay, and here the power is same as. So you need not to write this, guys. Already the name itself can give you the meaning. The name itself can give you the meaning. You need not to write this one. Okay. So the power is same as, even though it is one way restricted, the power is same as standard Turing machine. The power is same as standard Turing machine. Okay, next, guys, offline Turing machine. Offline Turing machine. Oh, you are online, na? This is offline. Okay. Now, what is offline Turing machine? In offline Turing machine, there will be a read-only head. There will be a read-only head. This is the infinite tape. But the thing is, the head is read-only. Read-only head means it cannot overwrite. Example, I want to accept 0 power 1 n 1 power n. What is the logic here? So whenever 0 comes, 0 को x करो, आगे चलो, 1 को y करो, पीछे आ जाओ, 0 को x करो, आगे चलो, 1 को y करो, ऐसा एक्ट करना. लेकिन read only means it cannot override. It can go forward and backward, but it cannot replace this 0 with x or 1 with y. Then how can it accept the 0 power and 1 power n language? Then in this case, whenever the offline Turing machine process the input string, I repeat, whenever the offline Turing machine process the input string, it takes the help of another tape. That is read-write tape. Okay na? So here it takes another tape. This is the read-write tape. So in this you can read and also you can write. Okay, this is read and write head. Okay, so whatever the input, example, here I am taking the input A, B, and these are the blanks. Okay, so here also A, B, blank. Then why, sir, why are you taking extra? Okay, so here this tape is the read only tape. So it cannot modify the input string. Whenever it process the Turing machine, the input string, it takes the help of another tape. that is read write tape. So with this read and write tape, it can accept, it can works as a standard Turing machine. Then why should we, takes the extra read only tape? You can say for security purpose of the input string. Okay na? Okay. So whenever it processes the input string, it takes the, it has read only tape. Read only tape. Whenever it process the input string, it takes the help of read write tape. Okay na? Take, and power is same as standard Turing machine. The power is same as standard Turing machine. Okay. So next, jumping Turing machine. So what is the standard Turing machine? After reading any input symbol, after completion of any transaction, the head, suppose this is the head, after scanning this input symbol, it can move left or it can move right only one cell. But after completion of the transaction, the head can jump to any cell from the present cell. Okay na? It can jump to, so after completion of this transaction, suppose it is here, after that it can jump to this cell also. Okay na? That is, and power is same as standard Turing machine. The power is same as standard Turing machine. Okay, next, copy. So remember, tomorrow class is 3 to 10. Okay na? Tomorrow class is 3 to 10, guys. चले next. So guys, next two more are there, that is read-only tape Turing machine and one-way Turing machine and halting Turing machine, linear bound automata. With this will be completed. Okay. Okay. Next. Read only tape Turing machine. Read only tape Turing machine means it can read the input symbol, but it cannot rewrite the symbol. Okay na? So if there is a tape, okay, it can move any direction. The head, but read only head. It can have read only head or read only tape. Okay na? Read only tape means it can move left side. After this it can move right side, but the symbol cannot be rewrite. So if symbol cannot be rewrite, so how can you accept these kind of languages? So which is not possible. So it can only read the symbol, but cannot rewrite. When it cannot rewrite, the power is not same as standard Turing machine. Its power is lesser and all equal to finite automata, because finite automata also it cannot rewrite na. That is the reason. Of course, there is a two-way DFA. It can move left side and right side. You can see the workbook. I will explain. So very soon I'll do the workbook. So most probably from Monday onwards I will go for the video solutions, and within 2-3 days, and Monday, Tuesday, and by Wednesday I will provide you the chapter 1, and within next 2 days I will provide the chapter 2 and chapter 3. Okay, next week I'll provide you the video solutions. You please go through the workbook until then. Okay, you try yourself. It can only read the symbol but cannot rewrite. So the power is same as finite automata. The power is same as finite automata. The power is same as finite automata. Okay, next. Got it? Next. One way Turing machine. One-way Turing machine. What is this one-way Turing machine? Copied or not? This one. One-way Turing machine. Here, the Turing machine, the head can move only in one direction. The head can move only one direction, either left or right. So it cannot. Example, I want to accept 0 power 1 power n. What is the logic? Push, convert the 0 into x, convert the 0 into x, then move right side until you get the 1. When you get the 1, okay, convert this 1 into y, then come back, but the machine cannot come back. The machine, the head, not machine, the head cannot come back. So because one way to the machine, are you following? One way, so it can move only in one direction. It cannot move left and right and left and right like that. So here also the power is same as Turing machine. The power is same as finite automata. Here I repeat, the head can move in only one direction. It cannot come back. So when it cannot come back, it cannot accept these kind of languages. Then the power is same as finite automata. What is the difference between here read-only tape? Here it can move left and right. It can move left and right, but it cannot rewrite. Here it can rewrite. Example, 0 can be x and forward, forward, and when 1 comes, we replace y, but it cannot come back. Okay, whereas it can come back and go forward and come backward, but it cannot rewrite. That is the reason power is same. Here also the power is same. Okay, so read one way only. The head can move only one way. So the power is same as standard Turing machine. Sorry guys, the power is same as finite automata. Okay. Next. So these are power are same as finite automata, read only and one way. Next. Non-deterministic Turing machine. Non-deterministic Turing machine. NDTM. Non-deterministic Turing machine. So guys, simple. What is NDTM? Suppose we have Q0, A. Suppose it takes a state and symbol. So if I write like this, Q1, X, right side. What is the meaning of this one? Q0 will be the state Q0, from the state Q0, the machine changes to Q1. A will be X, head moves right side. Suppose I write like this, Q0, A, left. What does it mean? In Q0, if A comes, then state can go to Q1, A will be replaced by X, head moves right side. Or Q0 will be Q0 only, A will be A only, head can move left side. So if there are any move has multiple elements, any transaction has multiple elements, then it is said to be NDTM. So what is the here the transition function? It takes a state and tape symbol. It may be tape symbol or input symbol. Of course, every input symbol also tape symbol. So into Q cross, tau cross, left and right, left or right, not left and right, and any finite combination, any finite combination. Okay, so q cross tau into q cross tau cross left and right. Example this one. Okay now. So it may have not necessary that everything will have multiple. It can have only one. It may not be defined. If it is defined, it can have one or more than one. It may be empty, undefined. If it is defined, it can have one or more than one elements. Okay. Now here even though it can have multiple moves, the power is same as standard Turing machine. The power is same as the power is same as standard Turing machine. Okay. Now here you remember every NFA is also DFA. Every NFA, sorry guys, I repeat. Every DFA, sorry guys, I repeat. Every DFA is also NFA. Every DFA is also NFA. But every NFA is not DFA. Every DFA is also NFA, but every NFA may not be a DFA. Similarly, here also every deterministic Turing machine, which is standard Turing machine, every deterministic Turing machine is also NDTM, non-deterministic Turing machine. Okay na? Every DFA is also NFA. Similarly, every deterministic Turing machine is also NDTM, but every NFA is not DFA. Similarly, but every NDTM is not a DTM, deterministic Turing machine. Is not a deterministic Turing machine. Okay now? Is not a deterministic Turing machine. Alright. Better you write as a deterministic Turing machine. Okay na? Here at least one place. Every deterministic Turing machine is also a non-deterministic Turing machine, but every non-deterministic Turing machine is not a deterministic Turing machine. Okay. Okay, now guys, every DF is also NFA, but every NFA is not DFA. Similarly, every DPD also NPDA, but every NPDA is not DPDA. Okay. Similarly, every deterministic Turing machine also and non-deterministic Turing machine, but every non-deterministic Turing machine is not a deterministic Turing machine. Okay, then done. Next. For every NFA, you can construct an equivalent DFA. For every NFA, you can construct an equivalent DFA. But every NPDA, we cannot construct a DPDA. I told you, for every NPDA, we cannot construct a DPDA. There is no algorithm for conversion of NPDA to DPDA. There is no algorithm for conversion of NPDA to DPDA. Okay na? But from NFA to DFA there is an algorithm, but NPDA to DPDA algorithm not there. And next one. So coming to non-deterministic Turing machine, every non-deterministic Turing machine can be converted into, I repeat, every non-deterministic Turing machine can be converted into deterministic Turing machine. There is an algorithm. Okay. There exists an algorithm to convert every NDTM to DTM, but there is no algorithm from NPDA to DPDA. So this algorithm we don't have, not necessary, not required. Okay. There exists an algorithm to convert every NDTM to DTM. Okay. Now, so guys, tell me the power of this NDTM is same as datamation Turing machine or standard Turing machine, because there exists for every NDTM there exists a DTM. Okay. Copy. Okay. Now, halting Turing machine. Halting Turing machine. HTM. Halting Turing machine. HTM. Okay. So guys, here in the case of a Turing machine, we have done one. I told you one case. Suppose there is a Turing machine, okay, and in the tape we have taken one input string. Example, this is the input string, blank blank. Now, whenever a string is given, suppose this is the language w1, w2, w3, w4, so on, wn, and so on, infinite. Okay. So when you take the Turing machine, if w belongs to L, means if you take a string in the language, then the Turing machine halts in a final state, stops in a final state, and implies W is accepted. Okay, na? What is the acceptance of Turing machine? What is the acceptance of it? The string. What is the acceptance of a string by Turing machine? It must start from the initial ID. Q naught W. Yesterday I told you. Q naught initial ID. Q naught W. This is the initial ID, and before and after blank. So before and after you can take any number of blanks. After that, after one or more moves, if the machine reaches a final state, okay, what is QF here? QF is final state. QF is a final state. Then the string is said to be accepted. This is what yesterday I told you. Okay, na? Therefore, guys, any string you take from this language, for this language, this is the Turing machine. Suppose then M accepts W. Then M accepts W means because this is the language and we have taken the string within the language, then M means Turing machine. The Turing machine accepts W and halts. Halts means where it halts in a final state. Whenever the machine stops in a final state, then only we say the string is accepted. Okay, na? Simply If a string is valid, the Turing machine stops in a final state. If the string is valid, the Turing machine stops in a final state. Okay. Now, if W not belongs to L, the W not belongs to L, then Turing machine rejects W. Rejects W means it don't accept. It don't accept. Rejects W. It rejects W. How it rejects? By reaching the non-final. By reaching the non-final means by stopping in the non-final, or by going into infinite loop. Means it may go for hang. Means it go to right side, left side, right side, left side, right side, left side, right side, left side, aisa. So if the string is invalid, if the string is not a perfect string, not a valid string, means not in the language, whatever the language you are taking, that string is not in the language, then the Turing machine definitely don't stop in final. Either it stops in a non-final, either it stops in a non-final, or it go into the infinite loop, means hang. Okay na? So if W not belongs to L, then Turing machine rejects W by halting in a non-final state, by reaching a non-final state, or by halting in a non-final state, or final state, or by entering into infinite loop. Entering into infinite loop. That is the machine hang. That is the machine hangs. Okay, it will hang. Okay now. So guys, now come to halting Turing machine. What is halting Turing machine? This is the discussion about the Turing machine, standard Turing machine. Whenever a string is given, if it is valid, the machine stops in a final state. And the string is accepted. If the string is invalid, the Turing machine may stops in non-final or may go to the infinite loop. Both cases we say the string is does not accepted, rejected. If W not belongs to L, then Turing machine rejects W by reaching a non-final or by entering into infinite loop. That is, the Turing machine goes to into hang position. Now coming to halting Turing machine. Halting, the name itself can tell you, always halts. If the machine is if the string is perfect, it stops in a final state. Valid string accepts. See, I repeat, if the string is valid, the string is accepted by reaching the final state. If the string is not valid, then also the machine stops. Means either valid string or invalid string. Always halting Turing machine stops, halts. If it is valid, it stops in a final. If it is invalid, it stops in a non-final. Simply, I repeat guys, halting Turing machine always stops for members as well as for non-members. Mean for valid strings, it stops in a final state. For invalid strings, it stops in a non-final state. Okay na? So the Turing machine always stops. So the halting Turing machine. The HTM is always stops. HTM, halting Turing machine, always stops for valid strings, as well as and invalid string also. For valid strings and for invalid strings also. So always always the halting Turing machine, always the halting Turing machine always stops for members as well as for non-members, for valid strings and for invalid strings also. Okay, na? For members as well as for non-members. Okay, so here the halting Turing machine, the power is lesser than standard Turing machine. Actually, halting Turing machine is used to accept, the halting Turing machine is used to accept recursive languages. Okay, na? Guys, the halting Turing machine is used to accept recursive languages, whereas Turing machine accepts recursively enumerable languages. Turing machine accepts recursive, I repeat, halting Turing machine accepts recursive and Turing machine accepts recursively enumerable languages. Okay, so take this one. So the power of HTM is lesser than the standard Turing machine. So halting Turing machine always stops for string. If the string is valid, it stops in a final. If the string is invalid, it stops in a non-final. Okay, na? So if W belongs to L, HTM halts in final. Means accepted. And if W not belongs to L, HTM now also halts, but it halts in a non-final state. That's it. That is the difference. It halts in a non-final state. Okay, copy this. Okay, so guys, if W belongs to L, then Turing machine accepts W and halts in a final state. If W not belongs to L, then Turing machine rejects W either by reaching non-final or by entering into infinite loop. Whereas HTM is always stops for valid strings or as well as for invalid string. So if a string is valid, it stops in A. If the string is valid, if W is, belongs to L, HTM halts in final state. If W not belongs to L, HTM halts in non-final state. Always halts. Belongs to L, stops in final. Not belongs to L, stops in non-final. Okay, and HTM is used to accept recursive languages. So note down this. Yeah, Turing machine is standard Turing machine or same determinate Turing machine. Turing machine means standard Turing machine as well as determinate Turing machine. Okay, That's all, guys. Tomorrow class is from 3 o'clock afternoon. Tomorrow afternoon 3 p.m. to 10 p.m. Okay.